Hello friends, welcome to GT Science tutorial. In this video, I'm going to explain about Frenkel defect in a crystalline slip. This is a very important defect and this is a part of point defect. And a similar kind of defect to it is a self-interstitial defect. You must have heard about that as well. So self-interstitial defect or Frenkel defect is very important for your bachelor's and master's degree. In this video, I'm going to explain what Frenkel defect actually is and we'll derive the mathematical expression for the Frenkel defect and we'll try to calculate the density of Frenkel defect, that is the number of Frenkel defect formed in a crystal. So let's start. First of all, let's try to understand what Frenkel defect actually is from its definition. So it was discovered by Jakob Frenkel. This was the scientist. He was the scientist who discovered Frenkel defect. Now, a Frenkel defect is a kind of point defect. It is a kind of point defect, and I already told you in a crystalline solid. A crystalline solid. So in this defect, what actually happens is that a vacancy is created at the initial location of the defect when an atom or smaller ion, typically a cation, moves from its usual lattice site to an interstitial position. Let's try to understand this with a sketch. Okay, you will definitely understand it in a simple way. See, these are let me try to make a proper drawing. So the bigger one is anion, the smaller one is anion. Okay, the larger circle is for anion and smaller circle is for cation. So you can see over here, I have made a crystal lattice over here. Okay, so smaller circles are these are cations, because we know that smaller like cations are smaller as compared to anion, and this larger circle anions anions. So you can see over here what actually happens in Frenkel defect is that from the crystal lattice a cation, because cations are smaller, will will create a vacancy and it will occupy an interstitial position. Interstitial position simply means it was supposed to be over here. It was supposed to be over here. This was its original position, but this will occupy some other position like this. See, this is the position that it it occupied. It was supposed to be over here, but it is now situating over here. This is the interstitial position. Okay, this is called the interstitial interstitial position. So this is a kind of defect in which an atom, simply a cation, will create a vacancy. It will lose its position and it will go in occupy an interstitial position. This is Frenkel defect. Now let's move forward. I hope you understood what Frenkel defect actually is. So consider a completely aligned grid of atoms. These are the grid of atoms or ions to be well ordered crystalline lattice. When a pawn means you can simply consider a smaller ion, jumps to a square that isn't its own. You can see over here, this was supposed to be its position. Now it is over here, leaving its original square empty. This is now empty. The resulting Frenkel defect is similar to be chessboard. You can consider it as chessboard as well. So let's move forward. Okay, so Frenkel defect in a crystalline solid. As you can see, why does it happen? What can be the reason? So the first one is size disparity. Size disparity means simply cations are smaller than anion. So that might be the reason for the crystal for the Frenkel defect. Similarly, low coordination number. You can get the screenshot over here. You can take the screenshot over here or you can make the note from here as well. Okay, so impact on crystalline properties. What could be the impact on crystalline properties? As you can see, the first one is electrical conductivity. So will there be any change in electrical conductivity? What do you think? So let's see what happens. Okay, because the mobile ions can aid in the conduction process, Frenkel flaws or defect can make ionic solids more electrically conductive. as we saw that as we saw that this ion was supposed to be over here. Now this is here, right? So this is free to move, And if an ion is there which is free to move, then obviously it will conduct more electricity, right? Now if you talk about density, is either the mass or volume changing? No, one atom is moving from here to here. That means neither mass nor the volume change. So density will obviously not be changed. So density will not be changed. So no discernible effect on its density. There won't be any change in density. Now, some examples can be silver halides, silver chloride, silver bromide, silver iodide. The reason for that is, in this case, anions are very large, cations are very small. This is the these are the examples of a Frenkel defect. Okay, now let's move forward to the derivation of Frenkel defect. So let's see the derivation. Okay, derivation. Derivation. If you have watched my previous videos about Schottky defect and vacancy defect, then this derivation will not be very difficult for you. It is a very small, simple derivation, but a little complicated steps are seen in this case. Okay, so let's start. Let's start from the simplest form. So first of all, we need to consider, we need to write the expression for the change in entropy, right? So the the change in change in entropy is given as what is the formula for the change in entropy? Del S is equal to K into ln W. Equation number 1. What is the meaning of this K? Yes, you are thinking correct. This is Boltzmann constant. Boltzmann constant. This W means probability. The most difficult step is finding the expression for this probability. We know W. W is equal to C. W is the probability, like that which ion will occupy which position. Okay, now let's try to understand and try to make a expression for this. So you can see over here how many atoms are over there. Total n atom, right? Total number of atom is n. Now how many interstitial sites are there? There might be n I represents interstitial site. This is the number of interstitial site. Okay, so either this atom or this ion or this ion or this ion or this ion, any ion might take the interstitial position, right? Generally we consider about the cation, that means smaller ions, these ions. So there might be n total number of ions. Not only that, there are ni total position that it can occupy. This ion moved here, but it could move over here as well, it could move over here as well, it could move over here as well, here. So there is total ni position that the ions could occupy. So we need to write the expression of entropy by being very careful. This entropy will be first one for the total number of ions, that is ni factorial by ni factorial sorry n factorial into, not this, this one was supposed to be small n, just a second. Okay, so n factorial into n minus n factorial into, now for interstitial side, that is ni factorial by n factorial into n minus n factorial and I minus n. Okay, so in the first term you can see there is only n, in the second term there is ni. That is the only difference. Okay, now for this term we have already done in my previous video. Now this term is additional over here. Let us consider this to be equation number 2. Now let us use equation number 2 in equation number 1. So equation 1 becomes, what will be the expression for equation 1? That is del S is equal to K into ln W means how much? N factorial by n factorial into n minus n factorial into n I factorial by n factorial into n I minus n factorial. Equation number 3, right? Let's move to another page. So see, now we need to write the expression for Helmholtz free energy. Now, now the Helmholtz free energy change is given by Helmholtz free energy change is given by, that is del A is equal to del E minus T del S. This is the formula for Helmholtz free energy change, right? This is equation number 4. So del A can be written as this NE can be written as NEF. EF represents average energy required to create one Frenkel defect, and this N is the density or total number of Frenkel defect formed. Okay, small n means that, minus T into del S. Del S means what? You can see over here. What was the formula for this del S? This much, K, ln, and all of these. Okay, so K, ln, and all of this means n factorial by n factorial n minus n factorial into n I factorial by n factorial into n I minus n factorial, right? So we get this value. Let us consider this to be equation number 5. Now we need to differentiate this equation with respect to del n, right? Or to do like in a simple way, let's try to do in another way. First of all, let's try to find this value. This value here, we have this value over here, that is ln n factorial by n factorial into n minus n factorial into n I factorial by n factorial into n I minus n factorial. So look at here, we need to try to find this value over here. First of all, we need to apply the product law of logarithm, that is ln, it will be this much, n factorial by n factorial into n minus n factorial in plus ln n I factorial by n factorial into ni minus n factorial. We get this much. Now we need to apply another property of logarithm, that is ln a b by c will be equal to ln a plus ln b minus ln c, or minus ln c. This is the formula, right? So this behaves as a, this behaves as b, and this will behave as c, right? So it will be ln n factorial minus ln n factorial minus ln n minus n factorial plus ln n I factorial minus ln n factorial minus ln n I minus n factorial, right? This one is very simple. Now if there is ln n factorial over here, that is log n factorial over here, we need to use Stirling's approximation. We know the Stirling's approximation. Stirling's approximation is, what is the Stirling's approximation? Ln x factorial will be equal to x ln x minus x. This is the Stirling's approximation. So this value, okay, this value, this much, gave it over here. Now if we apply Stirling's approximation, and if we keep solving it and cancelling the like terms with different sign, then we'll get a term. I'll write I'll write the final term over here, because we don't, if I keep solving everything, then the video will be too long, too lengthy. Okay, so we get, what do we get? Okay, k ln n No, this one was supposed to be k, should be n. So it should be n ln n, n ln n minus n minus n ln n minus n, n minus n plus ni ln ni minus ni ln ni minus ni minus n ln ni minus n and minus 2n ln n. Okay, we get this much. Okay, I've just copied from the book. You will directly get this much. Keep solving till you get this much. Okay, so after this, if we put this value in the previous equation of del a, so del a will become nef minus kt n ln n minus n minus n ln n minus n plus ni ln ni minus ni minus n ln ni minus n minus 2n ln n. So we get this much, right? Now let's differentiate it with respect to small n at constant temperature T. So differentiating with respect to n at constant temperature. If we differentiate it with respect to small n at constant temperature, then we need to write it like this: del by del n del A at constant temperature T. So if we differentiate it with respect to small n, so in first term n will get eliminated minus, and if you differentiate it, I'll write the final value directly. You can keep solving it, you will definitely get the proper value. If you get this value, then obviously whatever you get, that is correct. Okay, this is the exact value that you will get after solving it. kt ln n minus n plus ln ni minus n minus 2 ln n. Okay, if you get this much, then whatever you did, that is absolutely correct. Now at equilibrium, this value will be 0, right? So at equilibrium, del by del n del a t will be equal to 0. So the right side value, what was the right side value we had? That is ef minus kt ln n minus n plus ln ni minus n minus 2 ln n 2 ln n. So we get this much will be equal to how much? 0, right? So ef will go this side, and we will get ln n minus n plus ln ni minus n minus 2 ln n will be equal to ef by kt. We get directly this much. Now see, we know that there is a rule for logarithm, that is ln x square can be written as 2 ln x, right? So we can go in reverse. 2 ln x can be written like this, so we can write it like this: ln n minus n plus ln ni minus n minus ln n square is equal to ef by kt. Now we can again use this formula. Product is this plus means ln this into this minus means this one will be in denominator. So we can write it like this: ln n minus n into ni minus n by n square will be equal to ef by kt, right? So if we remove this ln, there will be exponential on the other side. So n minus n into ni minus n by n square will be equal to ef by kt. We get this much, right? Now let's move to another page. We know n is much greater than small n. Also ni is much greater than small n. So n minus small n can be written as n, and I minus small n can be written as ni. So what do we get? So what do we get? This equation, in this equation, this small n will get cancelled out, right? Will get eliminated or neglected. So we'll get n into ni by n square is equal to exponential of ef by exponential of ef by kt. We get this much, right? Now this uh, n square, if we find a value of n square, we will get this much, and I into e to the power minus ef by kt, minus ef by kt, as this n square is in denominator. If we go it in, if we take it in numerator, then obviously its power sign will get changed. That is simple law of indices, right? If we remove this n sorry, square over here, then we need to put a square root over here, so it will be n I into e to the power minus ef by kt, kt's square root. So it will be n is equal to root under n into ni into e to the power minus ef by 2kt. This is the final expression for the total number of Frenkel defect produced in a crystal. Okay, and that depends on the total number of ions, total number of interstitial site, Boltzmann constant, absolute temperature, and EF. EF means average energy required to create one Frenkel defect. If it asks you in examination, that if the question asks to find out the relation for the Frenkel defect, either it's a density or number, they are asking the same thing. Okay, you need to solve the, when you need to solve the problem, you need to do the derivation till this formula, and that is your final expression. So that's all in this video. I hope you understood everything about this video. If you like the video, please share the video as much as you can, and thank you for watching the video, and please subscribe this channel to make my face like this. Thank you. Bye bye.